Okay, so we're now in a position where we can do the analysis, and I'm going to look at the first, I guess it's 51 traces. If you remember back to the video when we first did the point spectra, I took a single spectrum, that was this 1, 1 curve, and then I took 5 lots of 10 curves, and they were all sort of nominally over a clean part of the surface, although we didn't do that particularly carefully, so that some of them might have been over the top of a dimer, some of them might have been in the dimer trough, for example, and that would lead to slight differences in the spectra. But for the purposes of this analysis, we're just going to assume that we've got now 51, well, we've got 102 traces because we have got the forward and the reverse trace. I'm going to load all of those in. So I've cleared my variables, so I need to go back into the program control, say load all flat files into my data, and I'm going to load all of these spectra. So I want 2 down to 6. It wouldn't really matter if I left the topography waves in there because the spectroscopy analysis just wouldn't pick them up. But on the other hand, there's no reason to load them, so I'm just going to turn those off and click that one. So that I think are all of those first 51 measurements that we did. And now let me load those into Igor. Just take a second. Okay, so now we have all of those waves here into my data, and I will do display all waves. So you can see there's some variation in here. That's probably to be expected given that we didn't do the experiment all that carefully in this instance. So I'm going to average all of those 51 traces into a single curve, and then I am going to differentiate those curves. And maybe we could do a little bit of smoothing as well. Right, and so this is then our point spectroscopy measurement that we have for this clean area of our surface. Might be interesting to look at this on a log scale. This side here, this is our valence band, this is our conduction band on the right, and in the middle, this is in principle our Fermi level. So we're expecting, the band gap to be, the silicon band gap is about 1.1 eV. When you include the surface states, it gets even smaller than that. So this kind of looks a bit too wide. But part of the issue here is just how we're displaying the data. So if we look at this on a log plot, okay, it's still not fantastic, but it's a lot better. So you can see our noise floor is somewhere down here around 10 to the minus 12, and above that we're getting signal. In fact, if we did our measurements, a little bit better, maybe with a higher set point current, for example, then what I would expect is that we would be detecting a surface state here. So rather than this the current going to 0, this would actually, there's a surface state that comes down here to about 0. On the valence band side, we wouldn't see that, and we'd end up with a band gap of about 0.5 eV, which is what we expect for the surface states of silicon. So that is, within how accurately we've done this measurement, this is looking okay. So let's just make this look a little bit nicer. Then we can make the minimum here. Let's make that 1 e to the minus 12. I think the maximum is probably okay, but maybe make that 2 e to the minus 10. Maybe something like that might be better, where we can still see a little bit of the noise. Right, and then the other things we can do in Igor, if I double-click these axes, then for some reason Igor always puts this standoff on the axis. It's a slight sort of offset on the axis. I don't like that, so I always turn that off. I also like to have an axis on the top and the bottom, and I tend to like the tick marks pointing on the inside, and let's do that for the left-hand axes as well. Off, mirror on, and ticks on the inside. So you see that we already get a pretty nice looking graph. We can go to the axes labels. So this is the left axis. So this is now our DI dV. And if I go to the bottom axis, this is now our sample bias. And Igor knows what the units are. So you can see now that I've typed something in here, it's added the units for the bias up here, so that's a bias voltage. But I want that to appear in the axis label, and there's a command for that, so this \U. And you can see now it puts the units there next to the sample bias. I don't know if it knows the units for the current, no. So I think if this were the current image, then that would have amps in there. But I guess it hasn't known this is in Siemens, which is the unit for conductivity. But yeah, okay. So then maybe what else I might like to do is just increase the point size of the curve, and the graph itself. If you right click somewhere on the white region, there's this option here, modify graph, and you can in one go change the font. So if I put font size 16 in there, if I was using markers, I might change the marker size there as well. So that's giving me these larger fonts, this actually would, I think, okay. So let me do this. If I go to Igor and go save graphics, and I just want to save it as a JPEG, I'm going to save it at 4 times the screen resolution, and let's just save that onto the desktop. So that's graph 3. Then if I go to the desktop here, open graph 3, then this is the JPEG that's been saved, and that, if that's in a in a sort of a column width document, then that comes out looking pretty nicely. There are lots of other. What I also tend to do is I decide on an absolute width here for the plots. What you need to export it to JPEG and then save it, and then sort of see how it looks when you import it into your document. But then you can come up with the sort of standard width modes that you like, and for saving your images, such that you have the right resolution and the right point size and the right font sizes. The other thing that's nice is the way that you can do the tick marks in Igor. So this is just doing automatic ticks here on the bottom axis. Now we can change this. You can change it to be completely user-defined, so you define them in a separate wave, so you could make them whatever you like. But this computed manual ticks is quite nice. So the canonical tick, this is the sort of the 0 here. The tick increment. Okay, so if maybe I wanted to just have 0 and 2, then the tick increment I would make 2, and I could say minor ticks. Let's say I wanted to have 10 per every major tick. So then we've got 10 minor ticks here up to the major increment of 2, but actually it probably is better to have these increment, 1 and 2 and so on, and then this looks like way too many tick marks, so make that 5 or even just 1, something like that. And we could do the same for the left for the left axis. So this is a log axis. I'm not exactly sure how that works when you have a log axis. But anyway, so that's just to show you that really, one of the very nice things about Igor is you very, very quickly are able to make publication quality graphs. But that's not the main reason we're using it for the tunneling spectroscopy. You could achieve this with other methods. The main reason for using Eagle for tunneling spectroscopy is when we do the three-dimensional, the spatially resolved tunneling spectroscopy, so the CCI TS analysis. Okay, but that sort of shows then this measurement of our of those first initial kind of 50 or 51 measurements that we made. This is fairly reasonable. We've got a valence band edge here. This is now the imaging into the valence band, conduction band over here. As I said, if we had done the measurements a bit more sensitive, I would have expected a kind of a flat region here down to 0. You can see something's kind of starting to happen. And the reason that we're not detecting that is because either we don't have enough, the signal to noise is not good enough. So one thing you could do is increase the set point current. That will in effect bring your tip a little bit closer to the surface, and you will get larger currents in this region here. So we can't see the surface state here at the moment because the noise is greater than the signal that's coming from that surface state. So now, if you remember, the next thing that we did was we tried to take a spectroscopy measurement at the step edge, and unfortunately that led quickly to the tip degrading. But in any case, we can try and have a look at those data. So again, I'm going to just rename this first one here. Let's just call that my data first, just so that we don't I don't want to load the next set into that same data folder. And so we have here 7.1 down to 7.10. These are the IV curves that we took at the step edge. So let me load those in. So this is going to be my data step edge. And let's see. I don't expect this is going to be all that great because, as we said, the tip went bad here. Display all waves. Okay, so there's a lot of variation here, but let's just sort of follow through with it anyway. Let's pretend that the measurement did work well. We can come in here, average these traces. I'm just going to do exactly the same thing again. So differentiate them and smooth them a little bit. Okay, so it's not, obviously, this is not the quality of data that we need if we were really doing a measurement, but let's now, I can add the traces together. So I have a function, I can, if you just click these two windows, so those are the last two windows that were used, then I have a function here which is combine two graphs into one. I think if I click that, oh no, it actually gives me, yeah, it gives me the option. So this is graph 3 and graph 4. If I click that, it should give me a new window with both of the traces on. So that's just a little sort of quick window, excuse me, quick macro that I added for doing that quickly. But since I've gone to the trouble already to make this one nice, I actually would rather add the data directly to here. So that when I've averaged the waves, it's moved them into this data folder here called averaged. Okay, so here we've got IV, it's this one here, IV 7.2 averaged, differentiated and smooth. So this is IV 7.2 averaged, differentiated and smooth. So this is the wave that I would like to add to this window. So I'm going to select this window. So this is the one that I'm now working on. I'm going to go in here. These are the standard Igor procedures, and I can go here, append traces to graph. So here you see in this top part here, this is the the data folder that we're currently in. So we're currently in this my data step, but the wave that I want to add is in this data folder average. So I need to go back to root. Then I'm going to select averaged, and I want to choose here this IV 7.2 averaged, differentiated, smoothed. I'm going to add that. I'm just going to add it to the same. I want to plot with the same value, so I'm going to have it on the left axis. There's an option. I could plot it with a new axis on the right, but there's no reason to do that here. Okay, so that's the new plot. So let me double click that and give it a different color. I'm going to set the line width a little bit bigger. And yeah, so I think I can also reorder these. I think I'd probably prefer that one to be behind the red curve. And then we might want to add a annotation. So in this case, I want to add a legend. These are not very descriptive in terms of having the final output. So I want to have this one here was the step edge measurement, and the first one was the clean surface measurement. And I sort of want the clean surface one to come first, so I can just move that like so. Okay, so then we have this this graph that we could use in some publication, but you can see this has the you know, ideally we'd be looking for some variation here, but we're not seeing a whole lot of variation. Yeah, all right. So now the next thing, I think we took also some spatially resolved tunneling spectroscopy. So let's move on to look at that. Okay, so the next thing that we did was take a bunch of spectroscopy measurements in a line. We had 10 lots of 10 spectroscopy measurements that we made over a region of space on the surface that covered several dimer rows and dimer troughs. And that data started at spectroscopy curve 8. And so that runs then down through to spectroscopy curve at the end of 17. So I'm going to select all of those and just deselect the couple of topography images that are in that lot, and let's load those in. Okay, so it's taken a little while because this is now loading in 100. Okay, no, we're done. So my data, and let's call this my data underscore line. And I guess we can do just the same thing, display all waves. And in this case, we are actually expecting variation because we're intentionally measuring at places on the surface where the density of states the density of states is varying. So one way to quickly try and look at this would be to change the colors of these traces. We don't want to do that manually. If we go into packages, so it's graph, packages, make traces different. And then there are options here to change the trace of the colors. So maybe if we just click this, no comment, that's not working. Okay, what if I take this one here? So this is now varying the color of the traces, sequentially starting from black and going through to yellow. All right, so this also is not ideal. Maybe, yeah, okay. So you can see this is pretty rough what we're doing here, but you can see, you can sort of get the idea that these traces are being grouped. Probably what we want to do here now is to load in the traces in groups of 10. Okay, so I've just quickly loaded in each of the groups of 10 into separate data folders. And so now let's just go through. So this is the 10, the first group of 10. And so I'm just going to average those to get my first plot. Move down to the second one. Display all waves. Average them. So that's my second curve. And so on. So I'm just going to quickly go through here and do that for all 10. Okay, so that's all 10 of those data points now averaged. And as we said before, these should all be in this data folder here called average, so IV8, IV9, IV10, and so on. So we can use Igor's graphing function here, new graph, and I'm going to select each of these waves and plot them. Now I've got here the option, this is choosing the Y wave, and I have the option here to choose the X wave. The first option is calculated, and what that is when Igor saves the waves, it has the data values, but you also have the option of saving the range of its X values, if you like, so the sort of start and end, and the number of X value points. It doesn't have to be the case. You can have a wave that is just a list of numbers without the corresponding information about its X wave. But in the case of these, the way that the data has been loaded in with the macros that I've written, then they do have this calculated wave with them. So we need to leave it there. But if you had your current and bias wave separately, then you would have to choose the bias wave on the X over here. But okay, so we want wave 8. I'm going to add that, add wave 9, wave 10, and so on. Okay, and let's look at it. Okay, so now we can see these are the different curves that we're getting as we move along. That those 10 points, and you can see that it does appear to be a real systematic change in this case. Well, let's just check that it is systematic. So for your packages, make traces different, then we can choose one of these color scales, maybe this one here. So we're going from blue, through red, and then look. Okay, so we actually, if you go back and look at the video where we took the data, we kind of go from one diamond row to a trough to another diamond row to another trough. So you can see here we've kind of started at blue. It's kind of moved up with red, and looks like then we come back down here for yellow. So if this were a real experiment, of course we would do everything here a lot more carefully. All I'm doing here really is trying to give you a sense of what we can do with this data analysis. And I guess maybe just to finish this, we could then this data might be too noisy for differentiating, but let's just have a look. So if we manipulate, differentiate all traces, okay, so this is all of those traces again. You can see it is noisy. When you differentiate these curves, the little noise that's on each of the lines gets amplified. But let's try just smoothing that a little bit. That gives us this one here, and then maybe let's just try again, changing the color scale here. And perhaps we could also change to a log scale, 180 minus 12. Yeah, I guess this color scheme is not exactly the best. Anyway, I think you get the idea. So you can see this data is maybe showing that there's a state sort of around these energies, and that exists. Perhaps I don't know if this was over the trough or over the diamond row, but it exists for one and not for the others. So that's kind of the idea of doing a spatially resolved tunneling spectroscopy measurement. So that's one way you can do spatially resolved tunneling spectroscopy. Of course, doing a CATS measurement makes this even more powerful, as we will hopefully see when we look at the CATS data that we took.